Hi guys, Ms. Gitlin here. I'm going to try and make a video about what you're missing in class on Wednesday. So here's where we are in our pursuit of differential equations. We know where they are. We know how to solve basic ones. We know how to solve ones where we have to use u substitution in order to take an antiderivative. We know how to visualize them with a slope field, and now we also know how to solve ones with x's and y's in it, the ones that we can separate, right? We can solve separable differential equations, okay? So now, what is the purpose of solving these differential equations? Well, remember at some point in time we talked about how there is real-life phenomena that's easily describable with a differential equation, but not, and then we have to solve the equation in order to get the solution. So for example, remember when we dropped something off a building, right? And we started with a second order differential equation, which was acceleration equals 9.8. And then we anti-differentiated it twice and got the actual solution that represented position, right? So that's what we're going to do today. We're going to look at a real life phenomena that's it makes sense and it's easy to describe it with a differential equation. And then we're going to solve it and look at a solution. Okay, so here we go. Let's read. A quantity, this is called a very special DFQ. Okay, so here's what it does. A quantity changes proportional to the amount present, right? Let y represents the amount present. Constant of proportionality is k, and the initial amount that's present is y naught. Okay, so let's think about that statement. A quantity, wait, I have to select a pen. Sorry, 1 second. Pause. Okay, quantity changes proportional to the amount present. So quantity changes, that's telling you that it's growing, right, or that it's decreasing. And how is it growing? Proportional to the amount present. So in other words, if there's a little amount of y, so you have this little blob, right, it's growing pretty slowly. But if you have a lot of something, it's growing much faster, right? So like, there's little of you, you're growing slowly. There's more of you, you're growing faster and faster and faster and faster, right? So what does this make you think about? Maybe something like bacteria, maybe something about like money in the bank, right? So let's write this sentence. So this sentence right here, we're going to write this as a differential equation and then solve it and look at a solution, all right? So quantity changes. So I'm going to say dy dt, because it's changing at a certain rate, right? Proportional to the amount present. So here's my constant of proportionality, k, and then to the amount present, y. So the larger the y is, the faster it's changing, right? And then my initial condition is going to be 0, y naught. So initially there's y naught amount of stuff in there, okay? And then let's try and solve it. Is this a differential equation that you know how to solve? It certainly is, because it's separable. We could separate variables and go from there. So let's see. So I'm going to bring all the y's on this side. So I'm going to say dy over y equals k dt, right? So k is a constant. My t's are over here, my y's over here. And I'm going to go whoop and whoop, and then anti-differentiate both sides. So what is that going to look like? The antiderivative of dy over y is ln of absolute value of y equals the antiderivative of k, and our variable is t, right? So the antiderivative of k is going to be kt plus c, okay? And then I'm going to go ahead and plug in the initial condition, 0, y naught. So as 0 goes in for t, right, y naught goes in for this, so we get c to equal ln of y naught, okay? So c equals ln of y naught. And we're going to ignore the absolute value at this point because the initial amount of something is going to be positive. So where do we stand right now? ln of absolute value of y equals kt plus ln of y naught, right? Now we actually have to solve for y. So to solve for y, we're going to exponentiate both sides, right? We've done this in class before. And we end up with absolute value of y equals e to the kt times e to the ln of y, right? And then e to the power of ln of y naught, the e and the ln are going to cancel each other out, and we'll just be left with y naught. Again, this is a problem that we did basically just like that in class. So go look at your notes if this is confusing. So then the simplified version, because I'm running out of space here, is going to be y naught, right? That's from here, e to the kt, okay? And then we're almost done, but we have to, sorry, one second. We have to get rid of this absolute value, right? By saying y is going to be plus or minus y naught, e to the kt. And then my initial condition, right? If t is 0, y has to be y naught. And we're saying that y naught is positive here because this is a physical thing that we're talking about. So we're going to keep the plus. Okay, so the solution to this very special differential equation looks like this. Y equals y naught e to the kt. And at this point, you guys should be like jumping up and down and being like, wait, I know this. This sounds so familiar, right? What does this look like? I lost my pencil. This looks like A equals PE to the RT. This looks like PERT, right? This is how you see the equation when you're in pre-calc, because this kind of situation describes all exponential growth, right? Continuous exponential growth. The more bacteria you have, the faster it grows. The more money you have, the faster it grows, right? This is how we got the fact that exponential functions model this kind of a phenomenon. Okay, so let's think about where we started. We started with a quantity changes proportional to the amount present, right? And this was a very logical statement. And then we wrote it as a differential equation, and then the solution to that differential equation ended up being PERT, right? Where the rate at which my y is growing is the same as this k, this constant of proportionality. Okay, so now let's save this file and then we'll do a problem.